Welcome to The Explainer. Today, we are diving into what has to be one of the most magnificent ironies in human history. We're going to look at how the purest, most theoretical, and honestly most abstract branch of mathematics, a field that people studied for literally thousands of years just for the fun of it, suddenly became the ultimate shield for our modern digital lives. Let's get right into it and see exactly how ancient number puzzles evolved into the actual backbone of global cybersecurity.
Okay, to really appreciate just how wild this story is, we have to get inside the minds of mathematicians throughout history. The American mathematician Leonard Dixon once famously said, "Thank God that number theory is unsullied by any application." And you know what? He totally wasn't alone in feeling that way. The British mathematician G.H. Hardy also heavily prided himself on the fact that his work had absolutely zero military or practical significance. For the longest time, setting prime numbers was just the ultimate example of pure mathematics. It was art, it was philosophy, it was emphatically not meant to be useful.
In fact, this field wasn't just respected, it was put on a massive pedestal. The legendary German mathematician Carl Friedrich Gauss basically called it the ultimate intellectual flex, saying, "Mathematics is the queen of the sciences, and number theory is the queen of mathematics." For centuries, this specific branch of math was revered purely for its abstract beauty. It was the absolute epitome of pure thought, completely detached from the messy real world of factories, commerce, or warfare.
So, what exactly is this queen of mathematics anyway? Let's just lay the basic foundation here. Number theory is a branch of pure mathematics devoted primarily to the study of integers. We're talking whole numbers here, no fractions, no decimals, and arithmetic functions. Number theorists spend their time obsessing over prime numbers and the properties of mathematical objects built from these integers. They look at rules of divisibility, prime factorization, and how all these whole numbers interact in seemingly magical, yet logically rigorous ways. And that brings us to a very specific type of ancient puzzle that number theorists absolutely love. They're named after a 3rd century Greek mathematician named Diophantus of Alexandria, who actually made huge contributions to this field through a work called Arithmetica. So, a Diophantan equation is basically a polynomial equation with 2 or more variables. But here is the massive catch, the absolute deal breaker. The solutions you're looking for are strictly restricted to integers. You can't just punch it into a calculator and get some messy decimal. The answers must be perfect, whole numbers. Conceptually, this restriction changes everything. Think about it. If you graph a normal linear equation like 2x plus 3y equals 12, you just get a straight line. A quadratic equation gives you a circle. But in Diophantine geometry, we don't care about the whole line or the whole shape. We only care about the exact, perfectly placed points on those shapes where the coordinates are both integers. Mathematicians call these integer lattice points. So for a circle, finding a solution means hunting down exact whole number coordinates, like 3 and 4, that sit perfectly right on that curve. Now, these integer puzzles escalate in complexity really fast, usually across 4 main types. First, you have linear equations, which are simple combos like 3x plus 5y equals 17. Then you bump up to quadratic, involving second-degree terms. You might actually recognize Pythagorean triples here, like 3 squared plus 4 squared equals 5 squared. Third is Pell's equation, which is a super famous puzzle in algebraic number theory. And finally, the absolute most daunting type, exponential Diophantine equations. This is where the variables themselves are literally trapped up in the exponents.
To give you a real sense of just how unbelievably difficult these integer puzzles can be, 358. That's a big number. That is the exact number of years that Fermat's last theorem, which is a famous exponential Diophantine equation, remained frustratingly unsolved. The French mathematician Pierre de Fermat casually scribbled in a book margin that no 3 positive integers can satisfy the equation a to the power of n plus b to the power of n equals c to the power of n when n is greater than 2. It took 358 years of human mathematical progress to finally prove the guy right. I mean, we are not talking about simple riddles here.
Which brings us to the most fascinating pivot in this whole story. We've got these ancient Greek equations, right? And we've got all these historical mathematicians proudly bragging that studying them has absolutely zero practical application. So, how on earth did this pure, pristine math become the internet's ultimate bodyguard? How does a field focused entirely on abstract intellectual flexing become the literal thing keeping your bank account safe today? Well, the answer finally arrived in the 1970s, and the whole illusion of pure, useless math was completely shattered.
While Diophantine puzzles proved how unbelievably complex whole numbers could be, computer scientists and cryptographers realized something huge. They realized that other foundational concepts of number theory, specifically prime numbers and greatest common divisors, were actually the perfect mathematical bedrock for public key crypto systems. As the digital age suddenly expanded, securing our communication became absolutely crucial, and this ancient field of study instantly had a massive, real-world job to do.
To make this actually work, cryptographers lean heavily on a concept called modular arithmetic. It's basically working with finite sets of integers where numbers wrap around after they reach a certain modulus value. Think of it exactly like a standard 12-hour clock. If it's 9 o'clock right now and you add 4 hours, you don't say it's 13 o'clock, right? The numbers wrap around the face of the clock, and boom, you arrive at 1 o'clock. This mathematical wrapping trick provides a whole range of formulas for rapidly solving complex equations with massive powers, which is completely essential for encoding messages.
But the real magic trick, the core principle making modern encryption possible, is a one-way mathematical difficulty. See, it is incredibly easy for a computer to take two extremely large prime numbers and smash them together by multiplying them to get a massive product. But it is computationally exhausting to undo that process. Taking that massive product and trying to figure out what those two original prime numbers were, it's a total nightmare. That extreme difficulty in prime factorization is literally the lock on the digital door.
So here is exactly how those purely theoretical primes secure our data using the RSA algorithm. First, the system chooses two massive prime numbers and multiplies them together to create a giant product. That product becomes the public key that anyone can see. Then, using something called Euler's theorem, specific keys are generated so that a message encrypted with that public key can only be decrypted by using modular arithmetic and the secret private key. Basically, if you don't know the original prime numbers, cracking the code is mathematically impossible within any reasonable time frame.
Today, virtually every theorem in elementary number theory actually shows up in a highly motivated way in computer calculations. This isn't just an abstract theory anymore. Every single time you log in to secure online banking, sign a digital document, or buy literally anything online, you are directly relying on the RSA algorithm and public key crypto systems. That abstract curiosity of ancient Greeks and 18th century math nerds is actively working behind the scenes right now, maintaining the privacy of your daily life. It's crazy.
But I want to leave you with a bit of a mind bender. As new technological threats emerge, the relevance of number theory in cryptography is only growing. We know that our current encryption works because normal computers take way too long to factor those massive prime numbers. But what happens to global security when quantum computers fully arrive? We're talking about machines that could potentially solve these ancient integer puzzles in a matter of seconds. The race for post-quantum cryptography is already in full swing, and researchers are desperately hunting for even more complex number-theoretic problems. The queen of mathematics, it seems, still has plenty of work ahead of her. Thanks for joining me for this explainer, and keep exploring.